So we left off with this example. Got a couple things I want to say on the top, so let's go and this. So these practice problems, I originally had the answer key file, and it wasn't on like the home page. It was under the files tab, but not the home page. So I moved that over there yesterday. If you haven't taken that quiz yet and are still going over those practice problems, you're gonna have those solutions there. Some of you came to me and kind of asked me even ahead of time, kind of to work, like people stopped by yesterday to work through some of these. So these practice problems and answers will be very, very helpful with this first quiz. Okay. So that first quiz is set to be due at the end of the day on Sunday. Right. You've got that problem set, which is right here. That's due before we start class on Tuesday. Okay. So probably don't wait to do it Tuesday because you have to do it pretty early in the morning, right? So get working on that. If you haven't, if you run into any issues, like I said, I had a handful of people kind of stop by yesterday. I think it's pretty productive. Other than that, housekeeping stuff. We'll see where we get to today in class, but I'll probably after class when I get back to my office today, put up the next quiz. So quiz number 2. By all means, like focus on the first one in the problem set, initially, but I will get it up there and have it set to be due at the end of the next Sunday. So you'll still have plenty of time to kind of review practice problems for that. I put up the next set of practice problems and answers. It's just that after today, I think we will have covered all the material needed to kind of take that second quiz. So this one is a little bit, review kind of takes a little bit longer. So that first and second quiz are a little bit closer together. The rest of the quizzes should be a little bit more like 2 weeks spaced out kind of moving forward. Here we kind of only had like a week in between when I released quiz 1 and quiz 2. So that's kind of where we're at housekeeping wise. We'll use that regression in class do file. So when it comes to these problem sets, I had some people stop by yesterday. That problem set 1, all you should need, everything you should need to do that is in that review of statistics do file. Okay? Obviously, it's not the same variables, but right, any command or anything you need to do, there's some example of it in there. Same kind of thing once we get to the next problem set, it'll be any do file we've done since then, right? So I think eventually we'll have the regression in class do file, and then we'll have next week a multiple regression. Those 2 do files contain everything you need to do for the second problem set. So I'll never ask you to do anything where I haven't done it in a do file that I've given you class and that we've worked in class. Okay. Any questions for me before we dive into material here today? Okay. So where did we leave off? I think we worked through this example. Mind if I'm saying something that's incorrect, let me know. But we kind of had this regression where we were saying our kind of dependent variable, the thing that we are thinking is changing is income, and then our independent variable, the thing that's changing on its own, that as it changes, it impacts our dependent or our y variable on the left-hand side there, is going to be the number of days someone uses marijuana each month. So we did this example, yeah? Get some head nods. Did we not do this example? All right, so I might have gotten a little bit further with my other section, so we'll go back. So did we talk about interpreting the coefficients? We did leave off there, right? So we said the way we interpret coefficients is our slope coefficient is going to be the change, the expected change in y from a 1 unit increase in x. We then talked about the intercept is going to be the expected value of y if x is equal to, well, if we have kind of this equation, if we're making predictions for what y is going to be, kind of ignore this epsilon for a second, right? We just have this as the relationship. If you plug 0 in, 0 times anything is 0, the intercept would be the predicted value of y. So when we run this regression, there is some actual effect beta 1 of this x variable. We are estimating what that effect is using our sample data, right? So we talked about we're making these errors, right? For any one observation, just kind of a reminder of, no, I drew this out, so we'll just review it. A bit of black. So we had this scatter plot of our data. We're trying to draw a line that best fitting, right? The equation of this line, it's going to predict different values of y. And we're going to do that using this slope and intercept coefficient that we get from Stata. Okay, so we did run some of those regressions to Stata, correct? Yeah, we did look at that. I just think we didn't do as much interpretation. So once I get these values from Stata, I can then come up with predicted values of y. But we said for any one observation, if I just plug in x here, the predicted value could be a little bit off for this one observation. We call that our error term. So the actual y value would be the predicted y value plus this error term. Okay? So once we have these, we can start making this generalized interpretation of this is the change in our predicted y value. If y goes up by 1 unit, that's literally what a slope tells us, even not in this class. Okay? And then the intercept is going to be, where does the predicted y value start out at when x is equal to 0? Okay? Any questions on that idea before we put some actual variables, make it a little more interesting here? Okay? There we go. So I had this data set with income, it's just in dollars, and then this marijuana variable, which is the number of reported days an individual uses marijuana each month. The median here is 0. Interesting fact about drug use data. A lot of times, if you look at survey versus actual consumption, they're very underreported, right? So with that idea in mind, I ran this regression. And I don't remember if we got to this last class, but we've used conditional statements before. We can use them in regressions too. So here, I just wanted to run this regression for a single year. That way I didn't have to worry about like policies changing across time periods. I'm just looking at 1 year of data, and I can interpret my slope coefficient as the expected change in y, so the expected decrease in income here, from 1 unit change in x, or using marijuana 1 additional day each month, I would predict that income falls by about $253. That's how I would interpret that slope coefficient. Now, how do I interpret that intercept coefficient? Well, this is where we said Stata, it calls the intercept the constant, right? It's because it always, when we look at that equation, it always gets added into our prediction, right? So intercept constant, those two terms are interchangeable. So this would be the predicted income for when the x variable is 0, or someone who uses marijuana 0 days a month, will be about 32,000. Or you can say a specific number, but I'm just kind of approximating here. So that's how we start to interpret these values that Stata is giving us. Okay. Any questions on that? Shouldn't be too bad. We'll run through more examples throughout class. So here's basically a synopsis of what I just said. Right? If you want to have it kind of written down, this is going to be the error.
So if the slope was positive, the coefficient would also be positive, right? If there was a
yep, if like the one I drew, where we have a positive relationship, then it would be the predicted increase in y. So in general, we always say the predicted change in y, because it can be negative or positive. Just depends on the two variables we're looking at. Right? Questions? Okay. So I had this other example, which was I had this COVID kind of data laying around. It was county level data, and it had the percent of the county that was vaccinated. So this vaccinated variable is, the unit is percentage, right? 1%, 2%, et cetera. I then had the number of COVID cases per 100,000, not 100, 1,000 people in that county. I ran this regression where I was trying to predict the number of cases that the county saw based off of the percent of their population that was vaccinated, right? So I look at this, and how can I interpret my slope and intercept coefficient? Well, the intercept coefficient is maybe the easiest to start out with. It's going to be if I had what? It's when x is equal to 0. So if 0% of the county was vaccinated, the predicted number of COVID cases for 1,000 people was 50.9. Excuse me. So it's what? 5% of people were getting it. What if? How would I interpret my slope coefficient? Well, it's a 1 unit change in x. So here, if 1% more of my population gets vaccinated, the predicted decrease in the number of cases I saw was about 0.25. Okay? So it only reduced the number of cases per 1,000 people by about 0.25. That's from a 1% increase. Now, I can use these slopes to not just do 1 unit increases. That's what the actual value is. But what if I wanted to know, well, what if the county got 10% more of its population vaccinated? What's the expected change we would see in COVID cases there? This is the effect of a 1 unit increase, a 1% increase. What would the effect of a 10 unit or 10% increase be?
Is it linear? So we can just multiply by 10?
Exactly. All right, we can always scale up this effect to whatever size we're interested in. If we know the effect of a 1 unit change, we can find the effect of the 5 unit change by taking that coefficient, multiplying by 5. We want the effect of a 25 unit change. Take that slope coefficient, multiply by 25. Not trying to trick you there, just scaling up that effect. But the actual effect reported from Stata is always going to be 1 unit. Okay. Any questions on this before we can? We've got a lot of other stats that we're going to talk about, but for now we're just interpreting. Okay. I don't know if I did this last class. It's worth reiterating. I didn't have. It's hard to find sometimes examples like this. So if I think about number of years of education, maybe I've got some data that looks like this. And let's say I'm trying to predict income. Keep using income, I guess. If I had my line that best fit this data, well, the slope of this line, that's my slope coefficient. The intercept is going to be where it hits my y-axis. What do you notice is true about the intercept here? It is negative. So this is going to be a really weird interpretation. So let's say I had like a value to put to it. So let's say I found it was negative 10,000. How would I interpret that intercept? It's going to be the predicted income for someone who has 0 years of education. Right? Well, how can you have negative income? Right? It doesn't even make any sense. Sometimes our intercepts won't make a lot of sense, but it's usually because we have to think about this variable that we're looking at. Years of education. If I had a data set with people's years of education and income, would I see 1s and 2s in there? Those would be like kindergarten dropouts, right? That doesn't really exist. So sometimes the intercept will have kind of a goofy interpretation depending on like the actual variables we're looking at. Okay, once we get up to like reasonable, maybe like 6th grade dropouts, even if we see something in the data, we probably end up with some positive predicted income there, right? But the actual intercept could still be negative. Okay. Any questions on this? Yeah.
So we never truncate the y-intercept, right?
We still interpret it the exact same way, even if it's a little bit goofy. Yep. Any other questions on this? Okay. So let's go back. There we go. We're going to talk about another statistic that we see reported to us from Stata, which is the R squared, right? So this is going to be what we call the coefficient of determination. I honestly probably won't use that throughout the rest of the semester. I generally just always reference it as R squared, right? But basically what R squared is doing is it's measuring, so the original Y variable, right? So when I was trying to predict COVID cases, if I just looked at that Y variable, it has some original variation in it, right? Now we want to be able to make good predictions. If we could make perfect predictions, we could explain all of that variation with our chosen X variable. And if we can explain all that variation, then our predictions with X would be perfect, right? We would have no errors. Well, that's an ideal world. We never can get to that point, right? So what R squared measures is, okay, of your chosen X variable, how much of the variation in that Y variable was it explaining, right? So how much of the changes in cases, COVID cases, was I explaining just with the percent vaccinated? Okay? So kind of the actual math behind it, which we're not going to have to do this by hand. We're really trying to interpret these statistics. So the interpretation, what I just spent time is what I'm really focused on. But how do we actually calculate the R squared? Well, you would think about our total sum of squares down here. That's just going to, looks very similar to what? If I divide it by n, variance, right? It's essentially like the variance that exists in that original Y variable. So how much of that variation can I explain? Well, how much am I explaining? Well, it's going to be not the difference between the actual Y and the average, but my predicted Y values. Because my predictions are using just that variable that I'm using to explain Y. So our explained sum of squares is how much variation exists in our predictions, right? So if we take a ratio of those two, that's going to be our R squared, right? So if I could explain all of the variation in that variable, what would my R squared be? Well, 1. Right? Now, generally, I think when we look at Stata, we'll see our R squared is in decimal. A lot of the times when we write it out, we put it in percentage form just because that's the way we talk, right? We generally wouldn't say, we explained 0.1, the proportion of the data we explained was 0.1. We would say we explained 10% of the variation. So the actual R squared reported to us will be in decimal form. We can always scale it up to a percentage. So to kind of give an example, we did kind of look at this data last class where we were looking at births and then these shale wells, right? Oil shale wells. So once again, we can interpret these coefficients. If a county had 0 oil wells, these shale wells, the predicted number of births would be about 6,100. Right? I think this was at the county level. And then how would we interpret the slope? Well, every time there's a 1 unit increase or we see one more shale well in that county, we would predict that the births goes down by about 4, right? 3.92. Okay. So those are interpretations. But there's a lot of other things that impact the number of births in a county, right? The population, income levels, and we're not really factoring any of that in yet. So before we even look at it, how much of the variation are we probably explaining in the number of births by using the number of oil shale wells? Probably not a lot, right? Where our predictions are probably going to not be that great because there's a lot of other factors that are probably a lot more influential at predicting the number of births. Sure enough, we go up and look at the R squared there, out to the 4th decimal, it is 0, right? There has to be some positive amount we're explaining, but it's a very, very small amount here. Okay? So this would be a good evidence that we're not really explaining everything. That the number of shale wells is a pretty bad predictor of the number of births. If I'm trying to get good predictions about the number of births in a county, I probably want to go out and try to find another variable. Income, like I said, population, some of these other things. Okay. Any questions? Yeah.
At what value would you say, be comfortable saying it is explaining?
So we don't really have necessarily a cutoff. What we're going to focus on today, before we get to multiple linear regression, which once we get to multiple linear regression, we can use more than just one thing to make our predictions. Then we start to see R squareds pretty high, and we like to get them up in the 90%. I mean, if we have all this data, we can get pretty good predictions. Here, all we're going to use it for this week or module, this topic, is because it's just using one variable on the right-hand side to walk before we can run, is we want to be able to compare across different variables. So we're not going to have any thresholds here, though. I mean, any threshold you can come up with, this one probably fails it, right? It's basically 0. We're not explaining hardly any of the variation. But we'll look at some others that are a little more interesting. So I have the COVID one. Once again, R squared is just my explained sum of squares over my total sum of squares. So I'll kind of point this out to you in a second. Notice for this regression, the percent vaccinated, what percent of the variation in the number of COVID cases was it explaining? So the proportion that it was explaining was what? 0.042. So we were explaining about 4.2% of the variation there, right? 0.042, 4.2% of the variation in COVID cases was explained by the percent of the county that was vaccinated. Now, I said that the R squared is your explained sum of squares over your total sum of squares. You can actually grab those values from Stata as well. I might ask you, I might show you something in a problem set or in a quiz where I black out what the actual R squared is, because I want you to know where to find these things. So our explained sum of squares, here this SS, that's sum of squares, right? Our model is explaining, this is kind of our model's sum of squares or our explained sum of squares. The amount of variation that our model is explaining. And then if you go down to the total, that's just our total variation that exists in the data, our total sum of squares. If I take the ratio of the two, you can prove this to yourself if you have a calculator or Excel open. If you do this math, sure enough, you end up getting that R squared. Okay? So even if you didn't see the R squared from the output here, you can use the explained sum of squares from your model, divide that by the total sum of squares that it gives you, and reproduce that R squared. So just as a point, we're not going to focus on it a lot, but that residual. So another term that a lot of times we see for the error term is we often reference it as the residual, right? It's what's left, right? We made a prediction. It wasn't the same as our actual Y variable. What was left? What was our error? What was the residual that existed? So here, the residual sum of squares is going to essentially be everything that our model couldn't explain. So if I take a ratio of my residual sum of squares to the total, about what value would that be? So
Almost 1.
almost one, but I can actually put a specific value to it, which is if I'm explaining, we said what?
Subtract,
4.
yeah.
Yeah.
So 95, right?
Yep. If I'm explaining about 4.2% of the variation, my residual sum of squares, that ratio, the percent that I can't explain, should be whatever would get me to 100, right? So 95.8%. So we don't use that a lot, but just to kind of be complete in describing all the output that we're seeing here from Stata. Okay? And don't worry about the adjusted R squared for now. We won't talk about that until later on. Okay. Any questions on anything here before we keep moving? Trying to go relatively slow here. I think I've got just some more examples. Oops. Stata here. So I've got my regression a little bit in class. Oops. There we go. So we'll come down here and my file path should be the iDrive here. So hopefully this works. Otherwise, I'm gonna have to manually do it. And I'm going to use this. Okay. So once again, whoops. Your path is going to be different. It's mostly probably for a lot of you just going to be like this and then ECON 371 files or whatever you call the folder. But this just allows you, I had some questions on this. You can always have the data downloaded. And then at this point, you could just go to File, Open, and open that COVID County data from your OneDrive. But if you set that file path, and it's always, your file path is always going to be the same, if you keep using the same folder throughout the entire semester, then you can actually run the code I have here. You don't have to go through the interface. Whatever's easiest for you to do, you can do either one of those options, right? I just make it possible that if you want to, you can kind of use just the code I have here by kind of setting your path at the very beginning of the file. Okay. So here I had the cases that the county had in October of 2021 and the population of the county, right? This is just some variables that existed in the data set. Now, my R squared, the percent that I was explaining with just how much of the population was vaccinated was about 4.2%. What do you think is probably, I kind of have a comment here, but what's probably true about the population and the number of COVID cases? Well, you have more people crammed into a small area, it's more likely you're going to get proliferation of a disease, right? So we run this code and sure enough, our R squared here is like 95 or 0.95 or 95% of the variation is explained just by the county's population.
So, sorry, I know I'm asking a lot of questions.
You're fine.
The R squared, it's a really, really low number, like in the one that we saw before. That means that the two variables that you use to compare each other are, like, it's not a good, it might be more of a correlation rather than a causation.
It could be evidence of that. It could just be evidence, like there is that I can with the data we'll end up showing. There's definitely a strong correlation between the percent vaccinated in the county and the number of COVID cases. The problem is, even though it has a very significant effect, or like a statistically significant effect, what we call the economic significance, it doesn't have a large impact, right? It doesn't have as large of an impact as, say, the number of people in that county. So we would still say that it has, we wouldn't want to think about it as though it's not correlated at all, because it still very well could be. And in fact, it very could well be causal, right? It's just that, let me think of another example. So your income is definitely dependent on, I mean, it shouldn't be, but you can look at data sets and see that that gender impacts it, right? That, there is some type of gender discrimination that exists in a lot of jobs, a lot of career fields. There's definitely an effect there, but it's a very small amount, right? It's a very small number how much it increases that income. Your education level explains a lot more about the changes in income, right? So there are tons of things that matter, and just because the R squared is low doesn't mean that it's not something that we think is definitely a causal relationship, but it could be evidence, a high R squared is likely definitely causal or definitely has an effect. The smaller R squared, it would be more likely that maybe it doesn't have an actual causal effect on that variable, but it doesn't necessarily mean that. Does that make sense?
For sure. Yeah. So then with a 0 R squared, it wouldn't mean that, right? Or maybe I'm not understanding.
Technically not quite, it gets difficult, once we start adding in more variables, I think it'll make a little more sense. But you can think about it as, let's say I had 100 factors that influence something. It's definitely, like all of them, it's in my production process, so I know that each one of these 100 factors is gonna impact this output. Well, 99 of them might explain 99.999999%. That one factor doesn't mean that it doesn't have an effect. It's just that relative to the other things, it's small. So it'll make, I think once we start adding in more variables, we can see that we're trying to figure out which variables have what we call a statistically significant effect, and then use all of them to make really good predictions and get that high R squared. So we'll hold off a little bit until we get to multiple linear regression. It is a little bit goofy when we're only looking at one variable, but for now you can just think about it as, it's easier to think about it as higher R squared. This is a variable that's better at predicting that Y variable. That might be the best way to think about it for right now. Yep. Any other questions here before we keep moving? So we got that R squared. We could then say, okay, what if I just used this variable, and we'll talk about these in a second, but we've got something called dummy variables. Now, we already looked at them to do like conditional means. These are just 1-0 variables. So indicator or dummy variables, two terms for the same thing. So here I'm just gonna run this regression, which is the number of new cases that the county saw, and I think this was like a difference between October 2021 and October 2020. I think that's how that variable was created. So it's the number of new cases, and then just a 1-0 variable for, was this county considered to be in the South, right? So this might be the idea that you're in the South, it's less likely you're cooped up indoors, and maybe less likely that we have like COVID spreading as easily, right? So now our interpretation of the coefficient gets actually a little bit easier. Yeah, can you make it a little bit bigger? Can I make this bigger? I think. See if this helps make this bigger, and rerun the code. See if this. I don't think there's any way for me to blow up this, because this interface is kind of set to be what it is. I can try to point this out, and a lot of this I like put on the slides that will make it bigger. So we'll take a look at like regressions of slide 2 and try to make them, snap or screenshot and blow them up so it's easier to read these, because I get these numbers are kind of small. So that's why I have the do file as well. So if you can run it along with me, you can hopefully see it on your device a little bit easier. Yep. So if I look here, my R squared is 0.0021. So if I'm comparing that to this R squared when I was using population, which one is explaining more of the variation in my Y variable? 0.95 or 0.0, what was it, 0.02, 0.002? Well, definitely this one, right? That R squared is a lot closer to 1. So it still looks like there is an effect if the county is in the South. So the way we now interpret that slope coefficient, it's a 1-unit change in X. Well, if it's just a 1-0 variable, what would a 1-unit change be? Going from the 0 group to the 1 group, right? So being a county that's not in the South to being a county in the South, we would predict that the number of cases actually was a little bit higher. So my went against our kind of initial intuition. But to the question earlier, is this a causal relationship? It's evidence of a correlation, but we haven't controlled for a lot of other factors yet. That's what we're eventually going to do next week, okay? But for now, we can kind of think about just looking at that R squared as a pretty good barometer. We can kind of work through these. So I could like compare the two. So maybe I'm looking at that cases per person again. One, I'm going to use the dummy variable of the South, then the percent vaccinated from this regression. My R squared here is 0.17. Here, once again, was 0.042. So which of these variables explains more of the variation in the cases per person? Well, that would actually be this dummy variable of the South, right? The R squared is about, I'm explaining 18% of the variation compared to 4%, which was that vaccinated variable was explaining. Okay. Any questions before we keep moving? Let me see where it is at in the slides, because I kind of want to. Yeah, we'll use this example. I think it will make a little more sense. So with this idea of dummy variables in mind, right? Everything looks exactly the same. It's just that now our x variable, I'm just using the notation of d, so that's a 1, 0 variable, right? It's just a 1, 0 variable that we're using instead of something that's more continuous. And I said, how do we interpret this? It's like going from the 0 to the 1 group. So it's like the additional change in that predicted y value from being considered whatever that one group is. So if I have like, I got an example later, we'll look at GPA and whether or not they were a student athlete, right? So what is the additional change in GPA from being in that one group or being a student athlete relative to not being a student athlete? Or gender is another popular one, right? What is the impact of being male compared to non-male, right? So the example that I'll use for this, I'll have to draw this out here, is going to be, what if we're looking at height, right? And we have this gender dummy variable, or indicator variable. So a good visualization of this is going to be, it's kind of weird. So this was our x variable, just a 1, 0 for whether or not they were male. I really can only have two values here. I had a 0 and a 1. Here, if I had this variable of height, right? And I run this regression where I'm looking at height and its predictor is just this dummy variable of whether or not the individual is male. So just a 1, 0, 1 if they're male, 0 if not. The predicted height here, what would my intercept kind of represent? So if I had beta 0 here, beta 0 would represent what? The height for
Female.
Yeah, female or not males here, right? Because it's when the x variable is equal to 0, so that's when the individual is not considered male. The predicted height would be whatever the intercept is. You know, you just plug 0 in here and get, oh yeah, my predicted height would just be whatever the intercept is. Beta 1 essentially is like, it's the change in the intercept for that group, because it says being in the one group or being considered male here as opposed to not, what's the additional predicted value in height? So here, we kind of think about this would be kind of where male height would start out. So beta 1 kind of would represent to us the difference in the average height of females and males, right? If we were running this very simple regression, okay? Does that, any questions? I get it's kind of weird to graph this out because we only have two values, but I think it's just another way of seeing that kind of helps some people solidify that idea. So we can think of these when we're using dummy variables. They essentially beta 0 and then beta 0 and beta 1 would kind of represent these group means. Okay, so I had an example here where I ran a regression where I predicted GPAs with whether or not they were student athlete. So I've got this is at the college level, and we can see here if they're not considered a student athlete, the predicted GPA was about 2.6. This was not great, right? And then if they were a student athlete, what's the predicted change in their GPA? Well, it was about 0.28 points lower, right? So these dummy variable interpretations, I think, are maybe a little bit easier because the units is just always going from that 0 to the 1 group. Okay? And how much of the variation are we explaining? A pretty low amount, 0.008 or 0.8% was our R-squared there. So probably not the most explanatory variable, just are you a student athlete or not in terms of your GPA. In fact, there's another variable in that data set, high school GPA. What do you think is probably true about that R-squared? If I ran a regression with college GPA and I was trying to predict it based off someone's high school GPA, that R-squared is probably relatively, if somebody gets a 4.0 in high school, do you think they're likely to get, I mean, it's telling you something, right? It tells you their success at the college level is probably going to be higher, which is why, what do colleges ask you for? Your high school GPA, because they think it's a very good predictor, right? So if we were to run a regression instead of using this dummy variable student athlete, we ran it with high school GPA, we'd see a pretty high R-square there. Questions on this before we keep moving? Okay, perfect. I think so no more questions on this before we go to the next topic. So the next thing is a little bit trickier. It's pretty easy to use dummy variables on the right-hand side or as our independent variables. Our dependent variables, if they're dummy variables, so they're 1s or 0s, it becomes a little bit tricky. Or a little, I don't say just like trick, but it's just different. So what if our y variables are dependent variables? What would the units of our variable be, right? So if you're thinking about my y variable is 0 to 1, changes in that y variable, so let's say like 0.2, I'm moving between 0 and 1, what would that actually kind of represent? What would that units be? It's actually telling me about the likelihood that I belong to that one group, or based off whatever my x variable is, as that x variable changes, how much is the increase or decrease in the predicted value of that 1, 0 variable? How much is the probability changing that I belong to that one group? Okay? So we have a dependent y variable, we have a dummy y variable or a dummy dependent variable. We can think about the units of our y variable here are going to be in terms of the probability of belonging to that one group. And I say one group, the group that is put in as a 1 in the data set. So let's think of an actual example, might make a little more sense, right? So let's say I have my unemployment rate and it's in percentages, right? So 1%, 2%, 3.5%, that's how we're measuring the unemployment rate. And then the metro is just a 0 if the county is considered to be a metro county, 1 if not, right? So how would I interpret beta 1 here? So it would be a 1 unit change in x. So if the unemployment rate in the county went up by 1%, right? The units for that unemployment rate variable were percentages. So if it was up by 1%, the predicted change in the probability that the county is a metro county would be whatever beta 1 is. So it's still a 1 unit change in our x variable, but now the effect on the predicted y is it's a change in the predicted probability that that county belongs to that group that's coded as a 1. So if we have some actual values to it here, we run that regression. Every 1% increase in the unemployment rate would actually decrease the chance that this is a metro county by about 0.045. Right? So, we're talking about probabilities. So a reduction of 0.045, it's a reduction of 4.5%. So we can kind of go back and forth, but just like the R squared, the actual values we see in stata, these are all in terms of like the probability, right? Or the proportion of variation we explained from the R squared. Changes in the probability we belong to the one group. Everything's kind of in that decimal form in that state output, okay? Any questions on this idea? Okay. So here's kind of that interpretation I just said, right? 1% change in the unemployment rate or a 1 unit change in the x variable causes the predicted probability that we belong to the one group or considered a metro county to be whatever that value we found for that slope coefficient beta 1 was, okay? Or 0.045 here, all right? How do we interpret kind of this intercept? So I've got it up here, but I'll kind of talk through it. So we still interpret the intercept the exact same way. It's when this x variable is equal to 0, right? Here's the expected value for y. Well, now once again, our y variable is a dummy variable, so it's in terms of probability. So if we could find a county that had 0% unemployment, the expected probability that they are a metro county is about 0.6. Right? So we would still kind of interpret that the same, which is when the x value is equal to 0, it's just our units are kind of goofy with a dummy variable. Our units are now in terms of probability. Okay. Any questions on this idea? Getting scared, you guys are kind of quiet. If you have questions, questions in this class generally help not only you, but everybody else. If you have a question, there's probably someone else in here thinking about it as well, okay? We're good? All right. I'm gonna get all this up there and I'll kind of draw something out for you, then we'll go to the state here.
I have a quick question. So
Go
I
back.
already talked about how like interpreting some of these are weird because of what values could be,
Yeah.
but let's say there was a question about, well, what's the probability you're in a metro area if this is the unemployment and it's below 0, would you say 0 or do you give it -%?
So if you're running the dependent variable as a 1, 0, shouldn't be able to come up with a goofy example.
Oh, okay.
So yeah, so you're saying what if the intercept was negative here? So the only reason why that occurred before is because we'll take a step. So remember the data we had before was like a scatter plot? Can't actually draw a scatter plot because what's gonna happen with this data? Our y values are only 0 and 1, so we actually won't ever end up with that weird intercept. The intercept is always gonna be something that's above 0 when we have that dependent y variable. That's a good question, because like, because that would be really, it would be even harder to interpret these examples if that happened, yeah. Any other questions? So, I'm gonna throw all this up there and we'll talk through it. Just like with our sample mean, our sample coefficients, when we're grabbing these coefficients from Stata, we usually write them with like a hat over the top of them instead of a bar, but they are our predicted coefficients. There's some actual relationship between these two variables. We've just predicted it based off of a data set, right? So with these predicted coefficients, think about it, it's the same thing we could do that we did with the sample mean. I could go out, randomly sample 50 people, run my regression, get a sample coefficient. Go out, randomly sample another 50 people, run my regression with that data, get another coefficient. I could do that like 1,000 times. If I do that, the expected value or the mean of those coefficients should always be whatever the true population coefficient should be. So I'll draw it out here for a second, but it's basically gonna also follow a normal distribution. Right? As long as we kind of get over, you know, that central limit theorem, we can get a sample size over 30. Now, our standard deviation, we end up calling our standard error. It's a little bit different than what we were doing with the sample mean. So you can kind of see here, I mean, we've got like some of the squares, total sum of squares. We've also got some of the errors divided by n-2. So it gets a little bit different. We're never going to actually have to compute it. But you can think of it, the easiest way to think about the standard error is it's essentially just the standard deviation of those sample coefficients that you're finding. So maybe to make this make a little more sense, if I stack these, I think it'll maybe help us with this idea. So remember before, we said that if I've got a bunch of different sample means, they're going to be centered around whatever the true population mean is, right? As long as we get a sample size over 30, they'll be normally distributed around it. We also said that the standard deviation of our sample means would have been the original standard deviation of the data over our sample size. Same kind of thing. If I were to take a bunch of different samples, run my regression, and have like 1,000 different coefficient estimates, they would also be normally distributed. But they're going to be normally distributed around, well, here are sample statistics, sample means are distributed around the population mean. Now our sample coefficients will be centered around the true coefficient that would exist if I had the entire population data set. And then here we don't write it this way, but you can think about, well, we could come up with what's the standard deviation that exists in those coefficients. In general, we call this the terminology used at the regression level because it's, to be technical, it's slightly different than what we're doing here, but it's still trying to measure the same thing, which is the variation that exists in these estimates. We generally call this the standard error of beta 1/2, or those slope coefficient estimates. Okay? So standard error, standard deviation, you kind of can think about them as the same thing. In fact, I'll jump the gun a little bit, but is everybody good with this before I keep it moving? Okay. Also, I gave this spiel to my last, they're freshmen though, I feel like they need more help, so maybe this is, you've heard this before. But I knew this person who had like a neurological issue. And I was talking with them the other day, they teach, and they had to like relearn a bunch of stuff. And they were telling me how like through the process of working with like all these neurologists, they could watch and listen to things and still not able to get back to kind of where they were before. But as soon as they started to, even as they're watching it, write down exactly what they're saying, it really increased that neural pathway. I'm not a neurologist, I don't know what the term is, but like it improved those neural pathways and they were able to relearn things much quicker, and also made you realize the importance of when you're doing things in class. Like I use the dot cam a lot more now, right? And so if I'm doing something up here, I'm writing something down, even if it makes complete sense, it's probably going to stick with you a lot longer if you're also kind of drawing it out as well, right? So this is the idea of taking notes. Like I said, you guys probably found what works for you at this point. You're not freshmen, but I just thought of it and like that spiel. I think kind of sometimes taking notes on what I'm doing up here is gonna be help make the concepts kind of lock in a little bit easier. So we have those distributions. Remember what we were doing then when we had sample means? We had some assumed true population mean. We would then turn whatever sample mean we had into a what? So if I have a sample mean, in order to know how likely is it that my assumed true value is in fact true, what do I turn this into? This doesn't bode well for the quiz results. A z-score, right? We had to then convert it. We're doing this hypothesis test. For this hypothesized true value, we need to turn this into a test statistic, or we said in general we're using that z, that standard normal distribution, right? To kind of approximate, because we have data sets that are over 100 usually. Once I had that, I could then find my what? I've got my test statistic. I go to the z table, I look up the area to the right of it. That would represent. You guys are scaring me. Our p-value, right? Now, with a two-tailed test, what would I have to do? It's not just this area. Yeah, but that would have been equally as likely to find damning evidence against the assumed true value on the other side. So I would take this area, multiply it by 2. That would give me my p-value. I then compare my p-value to different alpha values, right? Our kind of threshold cutoffs are the 10, 5, 1% significance levels. So I had someone stop by my office yesterday, and I have a tendency to kind of go back and forth between these terms. So if I'm thinking about alpha, our kind of traditional cutoffs are, if something has a probability that falls below 0.1, 0.05, or 0.01, we're okay rejecting the null. We said these are also called the significance levels, which are just the same thing, but in percentage form. So the 10, 5, and 1% levels, right? So we can reject with 10% confidence, 5%, or sorry, 10 confidence, 10% significance, 5, or 1%. And they correspond to these alphas. Now, they also correspond to a level of confidence. So in general, when we're looking at like academic papers, and a lot of this stuff we'll talk about in this class, I'm using more often than not the significance levels, asking you what levels can you reject, what significance levels can you reject at? If you look at more mainstream media, because it just makes a little more sense to the general public, we would have, this is also synonymous with the 90% confidence level. So if I can reject at the 10% significance level, I'm really saying that I'm rejecting with 90% confidence. If I can reject at the 5% significance level, I'm rejecting with 95% confidence. And then the 1% significance would be I'm rejecting with 99%. Right? So this might be a good thing to have kind of written down in front of you if we ever kind of go back and forth between significance confidence levels. Okay. So how do we find this test statistic? And technically, if we don't approximate it, we said it was coming from the student t distribution. Well, that was we just took the sample statistic, or the sample mean, subtract the assumed true value of the population mean, or population statistic, and then we divided by the standard deviation of our sample means. We're going to do the exact same thing when we're thinking about this distribution of our sample coefficients. Now, we will almost, in this class, we will always use, and here it gets kind of weird because this isn't the intercept, this is going to be my assumed true slope coefficient, right? So this is going to be coming from my null hypothesis, which is that the true value of beta is going to be equal to some assumed true value, right? The true population coefficient, we're assuming it's a certain value, right? Now the value we will always use in this class is 0, right? We're always going to start out assuming essentially, if I assume that slope coefficient is 0, what am I assuming? So if that slope coefficient, I say it's 0, I'm saying the relationship between x and y doesn't exist, right? So we're always going to start out stacking the deck against ourselves, assuming there is no relationship. And then if our data shows that there is something that's inconsistent with this, then maybe we can reject that, right? So we're gonna do the exact same thing. Now, Stata will use the student t distribution for us. If I ever ask you to kind of, a whole lot of critical value compare, this is why the critical value approach starts to become less useful, because Stata is always gonna give us our p-values from these student t distributions, so we don't even have to worry about looking them up, right? So we're always gonna have the p-value, which makes the p-value approach a little bit easier, right? There's no sense in like having to go through the degrees of freedom for a student t distribution, and they're always gonna be different. Just use the p-value that Stata is gonna tell us. So where's it getting the p-value? Well, we're gonna end up seeing a very, whatever data set we have, we're gonna see one sample coefficient for that slope coefficient. We're gonna wanna turn it into a test statistic from that student t distribution. We do the exact same thing as what we were doing for the sample mean. It's just we are now looking at a different statistic. So we're gonna take not the sample mean, but we're gonna take our sample estimate for that slope coefficient. We won't subtract the assumed true value of the mean, we're subtracting the assumed true value for that slope, which I said is always going to be 0. And then we're going to be dividing by the standard deviation of our sample mean. Well, now I said it's not quite the same, but instead of the standard deviation of our sample mean, we're now going to be dividing by that standard error, or I said you can think about it as the standard deviation of that sample slope coefficient. So it's the exact same format, it's just now we're doing it for a different statistic. Okay? Once I have my test statistic, I can look it up in the table, take this area, multiply it by 2. We're always looking at 2-tailed tests for this class. You can do 1-tailed test, but I'm not going to make you do any, at least for these slope coefficients. But yeah, it's really the same process, just things look a little bit different. Okay. Any questions on this before we? So I've got something I want to show you. Show me slides. Okay, so this is where we kind of left off. Okay? Now I jumped the gun a little bit with this discussion of test statistics, but I think in this order it makes sense for you to see it. Yeah.
Or able to like run through a problem or.
Yeah. Yep. So just a little more information before we do, just to be complete in what I'm telling you. You can do left and right tail tests. Now here, so it doesn't get tricky with the slope, instead of using like beta, the assumed true slope, I was using this gamma. Like I said, in practice, ours is always going to be 0. So if we're subtracting 0, we essentially, our test statistic is going to become, I'll come back to this, just the slope coefficient we see from Stata over our standard error, right? Because we're always going to use that same assumed true slope of 0. So here's kind of our steps. They're the exact same as what we were doing before. We're just using a different, right? We could do the critical value approach, or we could use the p-value approach. Like I said, we'll see from the Stata output, it's a lot easier to do the p-value approach. So let's say I had that old regression, right? If I looked at that marijuana days variable, and I look at that slope estimate of -253, okay? What I'm telling you is if we assume that that difference is 0, our test statistic should simply be that estimate for the slope over our standard error. Well, notice there's another column in Stata that tells us our standard error. So all I have to do is take -253, divide it by 48, and I would get that test statistic. So if I left out the test statistic, but I gave you the rest of this output, you could reproduce it. Because we're always going to use that assumed true slope of 0. Okay. Now, what Stata does, what I won't expect you to do, I would never leave off the p-value, because then you would have to take that test statistic, find the degrees of freedom on a student t distribution, and then look it up in the table. You won't have to do that. I'll always give you what that reported p-value is, which here, that p-value is what? Basically 0, right? So can I reject the null at our 3 conventional levels? Well, is that p-value going to be less than 0.1? Yeah, so I can reject that 10% level. Is it less than 0.05? Yeah, it's 0. Is it less than, yeah, it's 0. I can reject at all of our conventional levels. What am I rejecting? I'm rejecting that relationship between x and y doesn't exist. I'm rejecting that slope was 0. I found strong enough evidence that there is some relationship between these two variables. So that's why when we're talking about like, is there an actual relation, we don't look at the R squared necessarily. That's gonna be somewhat of an indicator, but this is what's gonna tell us whether or not there's a statistically significant relationship between these two variables. And here, it's significant at every single level, right? 10, 5, and 1%, okay? Or said differently, with 90, 95, and 99% confidence, I can reject that null, right? I can reject that there's no relationship between these two variables, okay? Now, the actual standard error equation is gonna be, you look at the differences, like, so your error is the difference between the predicted and the actual y's. You sum them all up, you add them up, you divide by n-2. I'm not gonna dive into exactly kind of the math theory behind why, but it's essentially because we're using two variables now to estimate something. So before, remember, we were always doing like n-1 with sample data. That was because we were only ever using one variable to calculate the mean. We're now using multiple variables to calculate this one statistic, which is the slope. You don't have to worry about that too much, but that's what is floating around behind the scenes, how these standard errors are being calculated. Okay? But for us, we can just use them. We're always going to be able to get that from the state output. We don't have to worry too much about calculating these by hand. And I say not too much. You don't have to worry at all about calculating by hand. You can also do this for the intercept or the constant. So a little bit less actual application of testing the intercept. But we can say, okay, I've got a constant or intercept here. Can I say that it's statistically significant at our conventional levels? Well, this one, that test statistic is insanely high, right? So I can reject at every single level there as well. There actually should be a value there for that intercept, right? It's something other than 0. Okay. All right. Oh, so I've already mentioned this, but I just threw a little thing there. This is why I think the p-value approach is easier, right? Because I don't want to mess around with having to look up critical values and then comparing these test statistics. If it already gives me the p-value, I'm done. Now, the p-value it reports to me is always for a two-tailed test, right? And it's always for the assumed true difference of, not difference, assumed true value of that slope of 0. Okay. Got another one here, right? So notice if I'm looking at total shale wells and the number of births, so going back to that example we were looking at earlier, I take that coefficient, negative 3.9. Notice if my standard error is pretty large, what's going to happen to my test statistic? When I divide that coefficient estimate by my standard error, I'm going to be getting a really small test statistic, which means the area to the right or left of it, depending on if it's more extreme than it, depends if it's negative or positive, means I'm going to get a pretty large p-value. Right? So here I've got a test statistic that's almost 0, right? Negative 0.05, which makes the p-value 0.96. Can I reject at any of my conventional levels? It's nowhere close to being less than any of 0.1, 0.05. So this is a variable where I would say it doesn't have a statistically significant relationship with the number of births. It's probably not it's not a good predictor. The R squared told me that, but it's also statistically not even correlated with this Y variable. And then we're kind of having this interpretation. I just threw it on there to kind of be complete here. So what I want to do next, I think it's worthwhile. So I will get the file updated. I probably speak too much about things I'm doing in this class sometimes, but I thought this was an interesting thing to look at. Interesting way to see what we're talking about today. So last night I tried to code this up. I think it's working. If there's any bugs, I apologize in advance, but I think I've got it right. I think it'll help kind of make sense, right? So I've got this COVID file opened up. I'm going to go down here and I've got all this code. So I'm going to run the regression. Now this data set, it really technically is population data because I had every county in the US. So technically I had population data. So I'm going to run this regression. And I know it's hard to see. Once again, I apologize. But the true slope from the population data is negative 2.5 here. Okay. What I'm then going to do is I had a bunch of code written up to create this program that randomly samples 30 people. It then runs the same regression, right? But now I'm just getting a sample kind of slope estimate, right? It's just from these 30 people. I'm then going to save that, go back, open the file again, randomly sample a different 30, run the regression, save that slope coefficient estimate, do that 1,000 different times, okay? So that's all this code does. So I'm gonna run this. And I think here, I have it set to be 100 instead of 1,000 because I'm just not sure how long it'll take to run this computer. So it's gonna run this. We'll see how long it takes. Okay, not too long, so it didn't take very long. I'm gonna see if I can get this to run 1,000 times. Okay. Now, once I have this done, what I essentially have is this variable that is saved the slope coefficient from every one of these 1,000 different samples. So I'm then gonna find the mean of those different estimates for what that slope coefficient is. If what I told you is true, the mean of all of those slope coefficients, right, they should have been centered around the actual population coefficient that we got from that original regression using all of the population data. So I'm gonna summarize this variable. So it's got 1,000 different slope coefficient estimates. Notice the mean of those slope coefficient estimates, negative 0.252, which is the exact same thing, or at least very, very close to what the true population coefficient is. So once again, you can always prove these things to yourself with data, right? Now, I'm not expecting you to run simulations or anything like that. I just think it's kind of interesting to see it actually play out. And in fact, no, I forget what it's called. I think it's hist. If I did a histogram of it, pretty nice normal distribution here, right? Now, obviously, to be perfectly normal, I can't just do 1,000. I'd have to do like an infinite number of simulations to really prove that. So I can't really do that. But yeah, I think this is a pretty nice little snapshot here. Now, what should happen if I take a higher sample size? So instead of 50, no, instead of 30, I take 100, right? I should be just getting a more and more tight distribution, right? It should be more and more normal. So I'm going to do the exact same thing. If I do 1,000 samples and run this regression 1,000 times, save the slope coefficient estimate, the mean is, once again, really close to that negative 0.252. It'll be a little bit off because I'm only doing it 1,000 times. But then same kind of idea here. I kind of get this nice tight distribution. The values, the range of values that I'm seeing is much narrower if I compare that to the other. It looks different because it's, I don't have as many values that are further out, but it's kind of creating a smaller range of values that I'm seeing here because I'm taking higher sample sizes. All the stuff we talked about with sample means and what impacts those distributions, same things would impact the distributions here for our sample slope coefficients. So I'll repost that code so you have that. You just want to run it and kind of take a look at it, but you're never going to have to reproduce that part of it. I want to go up here. Actually, yeah. Also, just to kind of start thinking about what we're doing a little bit more. I have this weird regression up here, so I'm going to reopen this COVID county data. And I'm going to do this, take this variable, which is household income, and I'm going to calculate the mean of it. I'm then going to calculate the standard deviation and then create this new variable, which is taking the original income variable and standardizing it. So I believe this is something I asked you to do in that first problem set. I think there was a question where I asked you to standardize a variable. Or if I didn't, maybe it's coming in the second problem set. So all we're doing is we're taking the variable, subtracting the mean, dividing by that standard deviation. So it gets kind of interesting, but if I standardize this variable, I've now subtracted the mean from every single observation. When I run my regression now, so let's say I ran this regression without the standardized variable, getting like 0.0003. Right? If I run it after I've standardized this, notice I kind of get some values that are a little bit more like, it's really hard when I'm dealing with really large values, like the income, $1 change isn't going to be very much. So sometimes it makes more sense to standardize that variable, right? So now that, instead of saying the interpreting of the slope coefficient, for every time the household income goes up by $1, the expected percent of the population getting vaccinated goes up by 0.0003. Okay, well, this is a lot more relevant. If household income goes up by a standard deviation, right, a 1 standard deviation increase in income, my expected change in the percent of the county getting vaccinated would be about 4.89. Okay? So it just makes it a little bit more digestible to kind of present to people sometimes when we standardize these variables, okay? But notice what's true about my test statistic on that income variable. Did it change the statistical significance at all? Standardized variable was 19.85 was my test statistic. The original variable was 19. So it won't influence the statistical significance. It'll influence what we call the kind of economic, like just the interpretation that we're having, making it a little more easy to digest for a normal or a normalized population, right? This gets weird. I think one increase in household income, that's weird to think about. Like, that's not going to change a whole lot, right? But a whole standard deviation, that's going to be a little bit more relevant. You'll also notice the R squared doesn't impact that at all, right? So standardizing this variable doesn't really influence any of our kind of statistical measures other than the one that we interpret, right? Other than just the slope coefficient itself. Any questions on that idea? It's just something I wanted to kind of make you aware of. We might start using some standardized variables because the interpretations make a little bit more sense for us. Where are we at in time? All right, so we got a couple more minutes left. Let me see what I have here. There we go. So the next thing we'll do is connect this. We already talked a little bit about hypothesis testing. Just like with sample means, we can connect this to the confidence interval. So we can build confidence intervals for sample means, right? That was just, we took our sample mean, we want a certain number of standard deviations to the left and the right, we create our upper and lower bound, right? That was telling us with this level of 90% confidence, the true mean is somewhere in this range. Or with 99% confidence, the true mean, based off the sample evidence we found, the true population mean should be somewhere in this range. We can do the exact same thing for slope coefficients. All we're going to do is take that coefficient estimate we found, negative 3.92. We're going to go a certain number of standard deviations away that correspond to whatever alpha we've set. So if I want to say something with 95% confidence, my alpha would be 0.05. I have half of alpha, so alpha over 2 on each side of my interval. Stata won't even approximate this with a standard normal. It uses the actual student t distribution with the correct degrees of freedom. It then creates this upper and lower bound for you. Okay. So if I were to like leave this off and ask you to do it, know that those number of standard deviations away, you can always use the standard normal approximate values, right? We'll always have sample sizes that are well over 100, and so we can always use those standardized values of what, 1.65, 1.96, and I think 2.58, if we look at those three levels. And I have those like in a summary table in the slides, and got the Z table if you really want to look them up. So we can build confidence intervals here as well. So what do the confidence intervals tell us? So we looked at this confidence interval. It goes from negative 164 to about 156. With 95% confidence, I know the true slope value is somewhere in that range. Well, if I assumed that the value was equal to 0, we said based on our p-value here, can I reject the null? No, right? 0.96 is anywhere close to being less than alpha. So I'm not going to be able to reject the null, even if I didn't have that p-value. If I only had the confidence interval, because 0 falls in that range, that confidence interval is telling me that any value in this range could be the true population value. 0 is in this range, so we can't reject it. So you could actually make your rejection decisions using the confidence interval as well. If that confidence, and that only works because we're always assuming that it's equal to 0. So if that confidence interval ever doesn't include 0, you know you can end up rejecting the null. Got, I think, another one here. So we've got here include 0. Here I've got one where there's only negative values, right? So when we go back to that income marijuana usage one, there's only negative values in my confidence interval. So with 95% confidence, the true slope value is somewhere in that range. It does not include 0. So if I do a hypothesis test for 0, I should be rejecting at the 95% level. Sure enough, my p-value is 0 here. We said we would be rejecting. So you can use the p-value. You could use the confidence intervals that are reported to you. They will always kind of line up. The decision will line up because we're always using that assumed true value of 0 for the slope in our hypothesis test. Okay? Any questions on that idea? I'm gonna do a little bit quick, yeah.
So can you go over one more time why you can assume zero?
So the reason why why I can say zero couldn't be a possible value.
No, why zero is the like the assumed true value.
So you can use other values. So for instance, maybe I was like, if I'm interested in this effect, maybe I'm like, well, I want to know if marijuana usage has more than a $1,000 impact on the predicted income. You can use other values. We generally don't want to have any preconceived notions about what the relationship between two variables are. And so the best practices are you always start out assuming there just is no relationship, right? And that kind of, it's kind of like a scientific method thing where researchers want to find effects. Like they're all like, I mean, a no effect is interesting sometimes, but generally we're always trying to find effects. So the whole idea of the null hypothesis is we're stacking the deck against ourselves from finding this, right? We're going to start out assuming the other state of nature is in fact what's going on, which for us is going to be that there's just no relationship between these two variables. And then if we can find enough evidence to reject that, well, now we can say there's some statistically significant relationship between these two.
So like with your example, but if you wanted to see if 1,000, for example, if it goes up in increments of 1,000, that if you did find correlation, that would be correlation that increases more than 1,000, right? So when we use zero, we're effectively saying that there is some change.
Yes.
Okay.
Yes. And if I were to use 1,000, things become a little bit more complicated with my test statistic and comparing that with my confidence interval, because my confidence interval doesn't include that assumed true value of 1,000. And so then those decisions don't line up. But when we're always assuming zero, then the decisions line up. But you can do it for other values. In fact, a lot, this maybe going into the weeds too much, but a lot of times researchers, if they know, like for instance, I mean, we know that if you inject yourself with anabolic steroids, you're going to get some level of muscle growth, right? Like we know there is going to be an effect, but we want to know, is the effect more than a certain amount, right? And so those researchers probably wouldn't use zero because just inherently the question they have at hand, they know that there's a positive effect. They know they're only looking at one side of the distribution. But for us, we're just always going to use zero. It makes it a little bit easier. So kind of already mentioned this a little bit, but we'll briefly talk about this. When we use those p-values in the confidence interval, we're talking about statistical significance, right? There's a statistically significant relationship, between these two variables. Economic significance is, who cares if I find a statistically significant relationship if the coefficient estimate for something like income and marijuana usage is that if I use marijuana one more day a month, the predicted decrease in my income is $0.000000001, right? There's no economic significance to that. So we do want to look for statistically significant relationships, but we also care about the size of the estimate, right? If the size of that coefficient estimate for income and marijuana usage starts to become really, really large, well, even if it's a little bit weaker statistically, it's still something we want to be concerned with. Even if we have really, really statistically significant coefficient estimates, but the values for the coefficient are really small, it doesn't really matter, right? It doesn't really change a whole lot for us. So we kind of, in different examples, we'll talk about, the statistical versus economic significance. I kind of briefly touched on it a little bit. I wanted to focus on a little bit more here. Ideally, we get both, right? We find a statistically significant effect that actually is pretty large, right? Or is going to be something worth talking about. So I think that I'll end it here. Let me remind myself. Yeah, so I probably won't put up the next quiz until after class next Tuesday. Just have a little bit more material that I want to cover with simple linear regression. Well, yeah, I'll hold off on putting it up, but you can start looking at those practice problems. And then I'll release the quiz after class next Tuesday when we complete all of this material, and then we'll start on multiple linear regression, okay? So what's due at the end of the day, Sunday? So the problem set's actually not due until we meet in class. You get a little bit of an extra day there to come by office hours Monday if you want to. That quiz, right? I had the practice problems for a while, so that's due by the end of the day, Sunday, alright? Any other questions for me before we get going? Is anyone still having any issues with Stata? Perfect, alright. Have a fun, safe weekend, and I will see you guys on Tuesday.